Hello everyone, this is chapter 9.2 and is concerned with a more in-depth examination of the features we discussed about that proton NMR spectrum at the end of video 2, chapter 9.1. This lecture will consist of 4 videos. Each will address a feature of proton NMR that is used to elucidate the structure of an organic molecule. So the first we'll look at chemical shifts. In the second we'll look at equivalent protons, the third will be concerned with integrals, and the final video with the concept of multiplicity. If you remember back to our last video, we looked at the proton NMR spectrum of bromoethane, and we observed 2 signals at different chemical shifts with respect to the internal reference tetramethylsilane. This always sets the chemical shift value to 0 parts per million. So what gives rise to these chemical shifts? In the last video we talked about the difference in energy levels between 2 spin states, alpha and beta, of our protons in a molecule. Each proton in an organic molecule is surrounded by an electron cloud which generates its own induced magnetic field. Electrons are charged particles in motion also, and this induced field is opposite to that of the applied magnetic field of the NMR spectrometer. Protons in different chemical environments require different radio frequencies to resonate, because the actual magnetic field, this is called B effective, experienced by a proton is dependent on the surrounding electron density. Therefore, how the proton is bonded and to which other groups it is bonded has an effect on the radio frequency that it requires in order for resonance to occur. This is what we mean by a chemical environment. For example, when a chemical shift is closer to 0 parts per million on the right hand side, we say that the proton signal, typically an alkyl group, that's CH bonds, experience a net smaller magnetic field, that's the BF, than the applied field. The phrase used is that these carbon-hydrogen protons are shielded. Hence these protons require a lower radio frequency to cause resonance and are found upfield on a proton NMR spectrum. Whereas signals that are to the left of the spectrum are said to be deshielded from the applied magnetic field, and they appear downfield on a NMR spectrum because they require higher radio frequencies to cause their resonance. What do you notice about the 2 different proton environments highlighted in pink and blue of bromoethane? Pause the video and resume when you are ready. Look at these protons' neighbours. The blue protons, A, in bromoethane are bonded to an electronegative atom, which withdraws the electron density away from these protons. This means they resonate at higher frequency because they are deshielded and are found further downfield on our spectrum. Whereas the pink protons B are further away from this atom and are shielded by the blue methylene CH2 group. Let's talk about the effects of electronegative atoms in a bit more detail on the next slide. Let's see what happens to the chemical shift of a proton when it's attached to atoms of increasing electronegativities. The representative compound, that's the methyl X, where X is a different element or a different group of elements, highlights this effect. We can see the elements X underneath with their corresponding electronegativity values and the effect this has on their chemical shift. Remember, TMS is an internal reference and all other proton signals are in relation to this 0 ppm value. What is the effect of increasing the electronegativity on the chemical shift of a proton? Pause the video and resume when you have an answer. As the electronegativity of the atom X increases along this series, we see an accompanying increase in the chemical shift of that proton's NMR signal. This is because the chemical environment of those protons have become increasingly deshielded, so they resonate at higher radio frequencies and thus appear further downfield. These substituents can be individual atoms or groups of atoms and are collectively known as electron withdrawing groups. What is the effect of increasing the number of electron withdrawing groups on the proton environment for these organic chlorides? Pause the video and resume when you have an idea. Okay, the greater the number of electron withdrawing groups that a proton environment has a cumulative effect. The more deshielded that proton environment becomes, therefore the more downfield the chemical shift of the observed proton NMR signal. The final effect is to see what happens when a proton environment is moved further away from an electron withdrawing group. Here we see a decrease in the electron withdrawing effect, and this completely vanishes by the proton environment being observed by about 4 bonds away from the electronegative atom. It's not just electronegative atoms that have this effect, as we'll see on the next slide. The hybridization of the carbon and whether there are pi electrons also impact on the radio frequencies required to cause protons in these chemical environments to resonate. For example, the pi electrons in a compound, when placed in an applied magnetic field, that's in the NMR machine, will move and generate their own induced magnetic field. This induced magnetic field, particularly for pi electrons, can cause a phenomenon known as the anisotropic effect. The best example to consider when explaining this effect is benzene. The pi electrons in benzene circulate and create a ring current. The induced magnetic field that results from this ring current reinforces the external magnetic field, B0, which is supplied by the NMR machine. So protons that are nearby to this magnetic field are deshielded, and these benzene rings or aromatic NMR signals are very easy to spot. Don't worry, you don't have to memorize these chemical shift ranges. These will be provided via Canvas in a correlation table. Lastly, you can see that protons that are capable of hydrogen bonding, that's those attached to oxygen or nitrogen atoms, span a broad range of chemical shifts. These also have signals that appear as broad peaks. A technique that is used to see whether or not these are proton signals that have arisen because of being bound to oxygen or nitrogen atoms is to run the NMR experiment with and without D2O, that's deuterated water. Deuterium is an isotope of hydrogen and is not NMR active. When the protons connected to oxygen or nitrogen are replaced by deuterium atoms, these broad signals disappear. This is useful because it provides more structural information about the organic molecule you're trying to elucidate the structure for. Let's see a complete list of peaks on the correlation table. Here is an example of such a correlation table. The protons highlighted in blue represent the chemical environment of that proton. Hopefully you can see how this technique will be useful in providing key structural information concerning the protons and their chemical environments. Proton NMR can be likened to a jigsaw puzzle. So far I've given you the edge pieces. If we use this spectroscopic technique in conjunction with IR, I'm hoping that you'll see the usefulness of these two combined techniques in building up the picture of a molecule. Our next key piece of information concerns whether protons in a particular chemical environment are equivalent or not.
This concludes part A.
In this video we're going to consider what is a chemically equivalent hydrogen or proton environment. Here's a molecule called dimethyl sulfoxide. The sulfur-oxygen double bond is a sulfonyl bond and behaves in an analogous fashion to the carbonyl bond. This is a symmetrical molecule and has the formula C2H6SO. I've given an extended or an expanded view of one of the CH3 groups, and I've coloured each hydrogen atom. There are 6 hydrogen atoms all in all, so would we expect to see 6 peaks for this NMR signal? The answer is no. There is 1 peak, which means that the protons of our 2 CH3 groups are exactly the same. Think of it like this. When we rotate the carbon-sulfur bond, we have not affected the connectivity of these atoms. We've just rotated the bond. I could have done the same with the other CH3 group, but both of these groups are identical to one another, so there wasn't any point in doing that. Every proton in the CH3 environment is exactly the same. All 6 protons then give rise to 1 single peak in the NMR experiment, and this produces a single NMR signal at 2.6 ppm. Now what about if I change the central atom and add another CH3 group? This time we have the molecule trimethylamine. Note that like DMSO, this amine is highly symmetrical. Hopefully you can see a theme occurring here that will help you to correctly discern the number of chemical environments based upon the symmetry of the molecule. The more symmetrical a molecule is, the fewer unique chemical environments it has, and therefore will have fewer signals in its proton NMR spectrum. So, why isn't the chemical shift of these CH3 protons of this molecule in the same place as those for DMSO? Have a think about it, pause the video and resume when you have an idea. This time round, the CH3 groups are bonded to nitrogen. While nitrogen may have the higher electronegativity value when compared to sulfur, remember that the sulfonyl bond contains a pi bond, and this has a greater electron withdrawing effect than the single nitrogen atom does. As a result, the chemical shift for all 9 protons is less deshielded with respect to DMSO, and appears further upfield. Let's look at another characteristic pi system while maintaining this theme of symmetry in a molecule. Benzene is a planar molecule, and now in this molecule called mesitylene we have 2 single peaks. The connectivity of the protons in red are the same. Seeing as these are directly attached to a benzene ring, the electron density is withdrawn by the benzene ring from these protons. Hence, these protons are more deshielded and appear much further downfield. The CH3 groups, however, contain protons which are slightly further away from the ring, 2 bonds distance. These protons are still relatively deshielded and are found in a similar region as protons that are connected to either nitrogen or other pi bonds, i.e. a carbonyl bond. Typical alkyl groups, that's carbon-hydrogen sigma bonds, are usually further upfield than this. Benzene's electron withdrawing effect is very strong, thus this effect is transmitted to those protons attached in the 3 CH3 groups of mesitylene. Notice how 2 unique chemical environments produce only 2 proton signals. Let's increase the number of environments one more time and use a molecule with a little less symmetry. Finally, we have a proton NMR with 3 unique signals, which means that there are 3 unique chemical environments for those protons. All of the protons in any one of those environments are equivalent. Hence, this is why we have been observing only single peaks for each of these NMR signals. Also, we now have the effects of protons that neighbour both a carbonyl group and an electronegative oxygen atom simultaneously. The methyl ketone environment is the least deshielded chemical environment of the 3 and has an NMR signal at 2.15 ppm. The methyl-ethyl signal is at 3.42 ppm and is caused by the CH3 group in the molecule being attached directly to an electronegative oxygen atom. Yet this is not the most deshielded environment. we observe a double whammy of electron withdrawing effects by interpreting the NMR signal at 4.03 ppm. This is for the methylene group in the middle of the molecule. It's a CH2 group. This methylene group is neighbouring two electron withdrawing groups. That's the carbonyl group and the electronegative oxygen atom. Earlier, we said that these electron withdrawing effects are additive, and here is the evidence of that. A proton environment that is bridged between two electron withdrawing groups, producing a signal that is the most deshielded. The next time we look at this molecule, we're going to change tack and think about how the area under each of these signals provides more information about these proton environments and their relationship to the molecule on display.
This concludes Part B.
In this video we're going to look at the concept of integration. As the title slide shows, this is concerned with the counting of hydrogens on an NMR spectrum. So here's that same molecule again from the end of video 2. The methyl ketone protons are responsible for the signal that you see at 2.15 ppm. And the area underneath this signal is measured using a process known as integration. Thankfully, this is done by computers when the NMR spectrum is processed, and the area underneath this peak is 3 protons, which is exactly the same as the number of hydrogens as there are in that methyl ketone. When we go to the peak, the second peak, this has 3 protons as well, and this corresponds to the methyl ether peak. And then the final peak is the methylene protons, and that has an integration of 2. These correlate exactly with the number of chemically equivalent protons found in the molecule. On this slide we've revisited mesitylene again, and we now see the largest signal has 9 equivalent protons, which correspond to the 3 CH3 groups in mesitylene. When you get a signal like this one with a large number of protons, this usually indicates a high level of symmetry in the molecule. The number of protons here is divisible by 3. One can assume that there are multiple CH3 groups present in the molecule. The integral of this also matches that suggestion. What is the integral of the other signal? Pause the video and resume when you have an answer. There are 3 protons in this chemical environment as given by the integral, and these correspond to the 3 hydrogen atoms that are directly attached to the benzene ring. But is it always this straightforward for molecules involving a benzene ring? How many signals would you be expecting here? You'd be right for thinking 3. However, 2 of those aromatic signals overlap, giving a broad signal. The integral simply tells us that there are 4 protons in this aromatic environment, but it's not able to differentiate between them. Now, this is often the case with aromatic signals that arise from a substituted benzene ring. The molecule still has a planar symmetry. This time we have 2 CH3 groups which give rise to an integral with a peak area of 6. What about if we change the placement of these CH3 groups on our benzene ring to produce a constitutional isomer? Here we have that constitutional isomer where we've moved the CH3 groups to 2 other positions on the benzene ring. In so doing, there are now 2 planes of symmetry in the molecule, and the aromatic signal has become sharper. That is, all of those protons in green are now in identical chemical environments. They're chemically equivalent. The sharpness of that signal can help to provide clues about the substituents on a benzene ring and how they are arranged. Let's look at one more example containing a benzene ring. So here's a quick exercise and a concept check. Count up the number of protons in each of the chemical environments and match these to their integrals. Pause the video and resume when you are ready. you should get 18 protons for the orange signal, 3 protons for the green signal, 1 proton for the red signal, and 2 protons for the blue signal. Of course, the sum of the integrals will also tell you how many protons there are in your molecule in total. How might you check that the red signal belongs to the OH group? Pause the video and resume when you have an answer. If you said run the NMR with and without deuterated water, that's D2O, then well done. Here's one last example that shows how integrals can help us with a structural elucidation. On this final slide, I'd like you to consider the question here. Why might this look like the spectrum for ethanol as well? This is in fact the spectrum for diethyl ether. Pause the video and think about this. Resume when you have an answer. The bonding in the ether and the alcohol has the same type of connectivity. That's a methyl followed by a methylene group that's connected to an oxygen atom. However, diethyl ether has double the number of protons than ethanol. Because of the plane of symmetry in the diethyl ethyl molecule, all of the proton environments, that's the CH3 and CH2, are on either side of the oxygen atom and resonate in exactly the same way. If this was ethanol, we might expect to see 3 signals, which is true, but the OH broad signal can be quite broad and is easy to miss in the spectrum. However, the integration ratios for these molecules would be different. Diethyl ether has signals with an integration ratio of 6:4, one for each chemically equivalent environment, that's the CH3 environment and the CH2 environment. Very similar signals would also appear for the alcohol at these chemical shifts, but the integration ratios of the integrals in the ethanol molecule would have a 3:2 integration ratio. Not all signals in proton NMR spectra are single peaks, however. Sometimes the signals are split by neighbouring proton environments and give rise to a concept known as spin-spin splitting, spin-spin coupling, or multiplicity.
This concludes part C.
This video covers the concept of multiplicity. Multiplicity is often the bane of a student's understanding when it comes to proton NMR, and so this concept will require considerable practice on your part. You're going to encounter the NMR spectroscopic technique on a number of courses, including this one. Once you develop this understanding, you'll be better able to start suggesting fragments for molecules that you haven't seen as part of the structural elucidation process. So far, our discussion has not really involved the effect of any neighbouring protons, because all of the examples that I have used with you have been carefully selected to produce NMR signals which were all single peaks. That is, all of the protons in those environments were equivalent, but were unaffected by their neighbouring proton's environment. This was for the purpose of thinking about the number of chemical environments, the chemical shifts in which these signals were observed, and the integrals of these signals. In this proton NMR, we now see signals that consist of peaks of different height ratios for just one NMR signal. The first signal at 0 ppm is the internal reference tetramethylsilane. This is a single peak because all 12 protons in TMS are equivalent and are not split by their neighbours. Proton NMR signals that are split into peaks have neighbouring protons that are typically 2 to 3 bonds away, which are not in the same chemical environment. All of the proton environments in this given molecule have a colour and a letter. This is for reference, and you are encouraged to do the same when elucidating a structure of an organic molecule. The displayed formula used for the molecule in this example doesn't make the symmetry obvious, And so we need to look at the connectivity of the protons in these groups to see if the protons in a particular environment are equivalent to those elsewhere in the structure. For example, protons called D, that's the pink ones, belong to two equivalent CH3 groups. By looking at the connectivity of these proton environments in each of the CH3 groups, they are equivalent to one another. All of the carbon-hydrogen bonds in the CH3 groups are connected to a CH2 group, which in turn is connected to an oxygen atom. Hence we have an integral of 6H, which for this signal is split into 3 peaks. How is the signal being split? The number of peaks for this signal and all of the other signals in this proton NMR are given by a rule called the n+1 rule. This works by looking at the number of equivalent neighbouring protons, and I cannot stress neighbouring enough, and adding 1. So for proton environment D, each CH3 group is split by its CH2 neighbour. So n is equal to 2, so 2 plus 1 gives the 3 peaks that we see. Thus proton environment D, the CH3 signal, is called a triplet. We'll think about the integration ratios of their heights on the next slide. Let's now look at the CH2 groups marked as C. How many of these groups are equivalent? How can we tell from the molecule and the proton NMR? Pause the video and continue when you have an answer. I'm hoping that you said that there are 2 equivalent CH2 groups. And firstly, when we consider their connectivity, they are the same. Both CH2 groups bridge a CH3 group and an oxygen atom. Secondly, this is also evidenced by the proton NMR spectrum, which contains a series of 4 peaks for this signal. Coincidentally, the integral also happens to be 4 hydrogens. For the purposes of counting the bonds, I've included an expanded view of just one of these CH2 groups, C, with respect to its neighbours. The signal is split by 3 equivalent protons, which are 2 to 3 bonds away. Therefore, n equals 3 this time, so 3 plus 1 equals 4, and this is responsible for the quartet signal that we see for the CH2 group C. All of the other protons are more than 2 to 3 bonds away and so cannot split this group. Finally, protons A and B are not equivalent. Each gives rise to a doublet because they are the only ones that neighbour each other in a 2 to 3 bonds distance of each other. Therefore, each one of these protons is split by the other. A is split by B, therefore n equals 1 plus 1, which gives 2 and gives a and gives a doublet, and B is split by A, so n equals 1 plus 1, which is 2, and gives rise to that second doublet. Let's now account for the heights of these peaks for any given NMR signal. The pattern that we see for Pascal's triangle refers to the number of peaks in a signal and also provides us their relative intensity, or we could say integrated ratios. So here are some structures in the middle of this table, and these provide some fragments which will help you to elucidate a chemical structure. You should try to recognize these basic splitting patterns and their shapes. Remember in this diagram that HA in blue is split by HB in pink, whereas HB in pink is split by HA in blue. Though you won't be tested on the relative ratios and intensities, these splitting patterns follow Pascal's triangle, and this you can easily write down. Now, a singlet has a ratio of 1. So therefore the area that has been underneath those peaks that are a single peak is equal to the number of protons in that environment. But a doublet is represented by 2 peaks with a 1-to-1 integrated ratio. So therefore you'll need to look at both of those peaks for the signal and match that up to the number of protons in that environment. A triplet is represented by peaks of integrated ratio 1-to-2-to-1, a quartet by 1-to-3-to-3-to-1, and so on. Now there are additional splitting patterns which include a quintet, and that is for when n plus 1 gives 5, a sextet for when n plus 1 gives 6, and a heptet for when n plus 1 gives 7. However, when there are more than 5 peaks, these can sometimes be referred to as a multiplet. Now let's look at the last example. Why does the fragment of that structure show a doublet for HA, which is seen in blue on the left, and a heptet for HB, which is seen in pink on the right? Pause the video and see if you can explain this using the n plus 1 rule. Resume the video when you're ready to check your answer. With respect to the structural fragment present, the 2 CH3 groups containing the equivalent protons HA have the same connectivity to the central carbon. Seeing as all 6 of these are equivalent, they will be split by the neighbouring HB proton. Now there is only one neighbouring HB proton, therefore the signal for HA is a doublet because 1 plus 1 equals to 2. Now let's consider proton HB. This single proton has 6 equivalent neighbouring protons within a 3-bond distance. Therefore n equals 6, so n plus 1 is 6 plus 1, which gives rise to the 7 peaks. This we call a heptet. For completeness, see Pascal's triangle for its integrated ratios.
This concludes Part D.